Hi! This is not how I anticipated to start this stream. My name is Mark, also known as Smitty or Smitty Halibut. KR6ZY is my call sign. I just gave a presentation yesterday morning at the QSO Today Ham Expo put on by, QSO Today, Eric Guth, 4Z1UG. I did a presentation on audio building blocks, and I only had about 30 minutes to give the presentation, and I was not able to go into any details, and I promised everybody that there would be no math, even though I kind of lied. And I wanted to have an opportunity to go into some details on what... I just totally made my glasses worse. I wanted to have an opportunity to go into the details that I couldn't do when I only had 30 minutes to talk. So this YouTube series is going to be in an attempt to go into that detail. Today, I'm going to describe a project that I actually need at home. When I was in the Q&A for that presentation afterwards, so I recorded the presentation ahead of time, and we uploaded that, and that was watched, the pre-recorded presentation, which I think worked really well. And then we hopped on Zoom and did a live Q&A. And I noticed that this microphone was plugged into that laptop, but I was connected to Zoom on that laptop. So I got my work laptop over there and my personal laptop over there, and I was doing everything on my personal laptop, but the microphone was still connected to my work laptop. So apparently I was using this microphone, or potentially the microphone on the laptop, when I was doing the Q&A, and I didn't notice that until after it was too late. So what I want to build is something that you connect a microphone into, and it takes that signal and splits it and runs it off to multiple sources, or multiple loads, multiple destinations. In my immediate case, both my laptops. I want to have one microphone work on both laptops. In the not too distant future case, I may also want to split that to like my D700 VHF UHF radio, and maybe even my HF radio, and have the one microphone split to all those different sources. I already have the speaker audio from all of those being mixed and sent in to my nice headphone amplifier. The ham radio community, I don't talk too much about it, but I'm actually an audiophile, and I design audiophile headphone amps. And my current design audiophile headphone amp has 4 input channels, 2 USB DACs, 1 for each laptop, and then 2 line level inputs that I've adapted from my D700 from speaker out to line level out into one of the channels, and then my FT920 is the 4th input. And so I've got both my radios going into my headphones. So I already have a single set of headphones with all of this audio coming into it. Now I just need something to take my one microphone and split it out to all of those different things. Those of you who listen to the Ham Radio Workbench podcast may recognize a lot of this as something that George and Mike and VE3ON, and I can't remember his first name. Anyway, that they've been talking about on the Ham Radio Workbench. Similar use cases, not exactly the same, but very similar. Anyway, so I started prototyping something today. I wanted to kind of test some theories, and I had the parts, but I didn't have a circuit board, so I started prototyping on this circuit board. And I hate prototyping this way. I would much rather sit down and design a circuit board. This is going to be a relatively small one, so it'll be inexpensive to fabricate and have shipped to me. And 2 weeks from now, I'll have a thing. But I wanted to at least test the theory. Really quickly, USB is only used for power. So I just needed something that I could quickly get some power into the thing. 5 volts is plenty for microphone amps. And then it goes into a little bit of power supply filtering. Apparently not enough, and we'll go into that. There is a op amp right here. It's actually a dual op amp. One side of it is used to create a false ground, which is something we'll be talking about, and then the other side of it is the actual amplifier. Then here we have 2 3.5 millimeter TRS sockets that are just parallel connected. It's just a pass-through. So the idea being that you plug the microphone into one and then one laptop into the other. And that way the laptop handles all of the power. It handles all of the... because electric microphones need a little bit of bias power in there, DC voltage applied to the mic level to amplify some things. So these two are just directly connected. I'm letting the laptop handle all of that stuff. But then I've taken the mic level output, I don't know if you can see, but that one right here underneath that my finger is kind of pointing at, taken that mic level output and split out and created a very high impedance load. That might be what part of the noise. Anyway, I created a very high impedance load off of it, blocked the DC voltage, and then fed that into the input of an op amp. And then the op amp lowers the impedance, makes it able to drive a whole lot of other loads. And then the output of that op amp goes to a couple of isolation transformers. The two outputs, so each output is an isolation transformer, so that the ground on this mic chain is very independent from the ground on these. And a DC blocking cap on the output side of the transformer to block any bias voltage coming in from the other device. And then I just have two of those, and they're just in parallel. The op amp should be able to drive multiple loads at 2.2K, which is a pretty typical load impedance for an electric microphone. So you should be able to put several of those in parallel, and that op amp will still be able to drive it. So that's kind of what I built. There's the bottom of the board, just kind of some point-to-point wiring on the breadboard, and I really, God, that is not focusing, is it? This thing's just not meant to focus close up, is it? Anyway, that's the board that I designed, and there are definitely some problems with it, and we will go into that as I was testing it. So we're going to use this circuit. It's a very simple circuit. I'm going to try and fix some of the problems that I had with it, and we're going to use this as a project to explain some of the audio building blocks and go into details. That's the key. The detail that I didn't have time to do in the QSO Today presentation. So let's get started. I use KiCad. It's my preferred package for this. Eagle is also very good. I know Eagle is a sponsor of the Ham Radio Workbench podcast, and even before that, it was George's preferred tool. That's just the system he uses. I got started on KiCad, and it's what I use. So I've already got the project set up. Let's go into the schematic. That is a very tiny window. That is still a very tiny window. Okay. So the first thing we're going to do is we are going to look into power, because that's the part that I think I'm having problems with. Excuse me, on this board. USB power is notoriously noisy. It is horrible. Absolutely horrendous. There are ways you can clean it up, and I tried doing at least a little bit of passive cleanup on this, and apparently it wasn't anywhere near enough. So we're going to look into that. I'm also going to make it so that it can be powered with an external power supply. So let's go ahead and drop a USB. No. Sure. No, actually, let's do this correctly. We're going to go ahead and use a USB micro connector. I just had these, the male USB A's, the big rectangular ones. I just had those in my parts bin, and I've got these little USB extension cords. So that's what I've been using for powering just this one, because it's a part that I have on hand. But let's do this one right. We're going to go ahead and do USB micro, and then more importantly, 1X02. So we're just going to give a pin header that can also be used to provide power. Normally I talk about KiCad and how to use KiCad. I'm not going to go into the details of how to use KiCad this time around. I'm going to be concentrating more on the schematic. So power in, and oops, nope, power. All right. I'm just going to treat these as parallel. So the way we're going to design this power circuit is that it is not going to be specific to any one particular voltage, and I'll show you what that means in a little bit. But I do want it to work on 5-volt power. So, but the 5-volt, let me rephrase. I do want it to work with only 5 volts on the input, because the USB only provides 5 volts. So let's go ahead and do this, plus 5 volts. We'll put that right there, and we'll copy that and put that down here. We are literally only using the USB for its power. Ground. Yeah, we'll just do ground. And we're going to make a different ground a little bit later. There, and we'll go ahead and ground the shield as well. All right, so there are our power inputs. We're just going to leave the digital lines completely disconnected. We're not doing anything with the digital lines. All right, so let me show you what I tried to do. So, one of those, and then a CP small. Value 2 microfarads. Okay. Then what am I going to call that? I can't just call it 5 volts because it's already taken. You know what I'm going to do? I'm going to do it differently. Hold on. I'm going to move that over here. I'm going to delete that. Okay, so this is what I tried to do. And then I use this 5 volt as my power supply for the rest of the circuit. The idea here being that the combination between that resistor and that capacitor makes an RC circuit. I told you in that presentation that we weren't going to be doing math. Let's do math. Nope, you don't want that one. I'm old school. BC minus L. So 1 over 2 times 3.14 times R, which is 10, times C, which is 220 microfarads. So that would be 1 millifarad. That would be 1 microfarad. And then I want 220 microfarads. Yes. So 1 over 2 pi RC. I have a better way of doing that on my phone, but you can't see my phone, so I'm going to do it here. 1 over 2 times pi times R, which is 10 ohms, and C, which is 220 microfarads. That's going to give us our frequency in the frequency of the RC value of this. The idea being that this is a capacitor to ground, that's a shunt, low pass filter. The idea being that we are going to, well, I guess technically it is a high pass filter to ground. So we are taking all of the high frequencies and shunting them to the ground. That's the idea behind having this R and that C there. The reason you have this R here is that you need to have something, you need to have some impedance between the noise that's coming in over here and the load that looks like this, right? The load is here. That resistor right there is the rest of our circuit. And if this resistor wasn't here, then we'd just be trying to use the resistance of this trace to drop the voltage of the noise. We're trying to get rid of the noise. We're trying to give the noise a place to drop, to get rid of that voltage. And so 10 ohms here into that 220 microfarad, in theory, will shunt, up to 72.4 hertz. Well, 72.4 hertz is the 3 dB down point. So anyway, the idea, it's a simple RC noise filter, right? And it didn't work. All of the noise that I have in there just passed right on through that. I might have been able to fix it if I put like a 10 microfarad and a 1 microfarad and a 0.1 microfarad and a 100 puff or something like that. Put a bunch of different values of capacitor in parallel. But really, what you need, you'll still get some of that through. Really, what you end up needing is a regulator. So let's move that out of the way. Let's get a regulator in here. 1117. I think those are the regulators that I want. So let's go to 3.3 volt regulator. We can get a little surface mount fixed 3.3 voltage regulator. And so the point of this regulator is to kind of actually serve the purpose of this resistor here. Actually, you know what? We don't even need that anymore. It's to serve the purpose of this resistor here. The idea being that it is a place for voltage to drop, so that coming in, you can have all kinds of noisy voltage coming into the thing, but it has a very fixed voltage reference internally, and it's forcing everything on the output to be at that fixed voltage. So you can have all kinds of noise on the input. The output voltage isn't determined based on the input voltage. The output voltage is determined based on the voltage reference inside the chip. And that doesn't change regardless of what voltage is coming in on the input. So voltage regulators have a property called power supply ripple or rejection ripple, PSRR, something like that. Anyway, there's a parameter that says how good is it at ignoring and eliminating the noise coming from the inside, from the input. And actually, that probably doesn't need to be 220 anymore. We can probably make that a 10 microfarad. And the same over here. Okay, so and now the power that we're actually going to use for the rest of the circuit is going to be 3.3 volts. All right, so that is the beginning. Oh, we can get rid of that one. We don't need that anymore. So that is the beginning of my circuit. This is the main power supply. We got power coming in from whatever we want, either a USB port or just like a 2-pin connector. We can hook up like a 5-volt wall wart to that, or we can do 12 volts if we wanted to, although 12 down to 3.3 volts would be a lot of voltage regulation, a lot of voltage drop. However, we're going to be drawing so little current that still isn't going to be dissipating much power. Because let's say we put in 13.8 volts here and we have 3.3 going out. That is 10.5 volts that are being dropped across this voltage regulator. And if you're pulling, we'll call it, go completely excessive. Let's say it's 1 amp. If you're pulling 1 amp through that voltage regulator at 10.5 volts drop, you have to dissipate 10.5 amps, or 10.5 watts, excuse me, which is a lot of power. We're not going to be anywhere near an amp. We're going to be closer to like 0.01 amps. So that would be like 100 milliwatts, right? So P equals IV. P equals IV. So power equals current times voltage. So the voltage drop across that device times the current going through that device is the amount of power that that device has to be able to radiate. Our power consumption is going to be very small, so I'm not too worried about that. All right, so this gives us a very cleanish 3.3 volt power on the output. I'm going to add one more capacitor to this. And I'm going to do a 0.1 microfarad. C small. So the CP small is a polarized cap, like an electrolytic. This one is a non-polarized cap, like a ceramic or similar. Okay, so now there we go. So now we got a nice and clean power supply. But we're not done. So this has cleaned up the power we're getting from our source. Audio. Audio is a little bit weird here. I'm going to go to camera only. Audio is a little bit weird. If you're used to dealing with digital circuits, you have power, or like power and ground, right? You got plus 5 volts or plus 3.3 volts and ground, and everything is typically between those two. You can do analog signals between ground and power and all of that stuff. But if you've got a signal that is outside this range, either above your power supply rail or below ground, that causes problems. And audio signals like, you know, line level signals on 3.5 millimeter TRS connections, the headphones, your headphone connection, your microphone, all of those things, they are all ground reference, which means here's your ground, and the voltage goes above the ground and below the ground, above the ground, below ground, above ground, below ground, which is fine from a signal perspective, but it does mean that if all of you've got is a ground and a plus 3.3 volts, I can deal with all the signal that's above ground, but I cannot deal with the signal that's below ground. I can't amplify it. I've got no voltage down there. It's outside my voltage range. There are two different ways of handling this. One is to have positive and negative supplies. So you have a solid rail, and you have like a plus 12 volt supply and a minus 12 volt supply. This is how I do my audiophile headphone amplifiers. I'm building my own power supplies. I got my own transformers, my old voltage regulator, bridge rectifiers and voltage regulators and all that fun stuff. So I can build my own supplies, and I have done so, and we've got plus and minus voltage supplies. So I can have a solid ground all the way through my signal path, all the way from the input to the outputs. And I have a real honest-to-goodness ground zero reference. Here we don't have that, and I don't want to complicate the voltage supply requirements to say that not only do you need to provide a plus 5 power supply, but you also need to provide a minus 5 volt power supply, because we can't do that with USB. That's just not an option with USB. So what we need to do is we need to create a new ground reference, and I'm going a 0 point of our audio. And we need to create a new 0 point for all the audio path that we're going to be doing any active circuitry on. So we're going to have an amplifier in here, so we need to define a new 0 point for our audio. And then we need to convert all of our input audio to that new 0 point. And then we need to convert the output of our signal to back down to ground when we leave our circuit. So we've got a little bit of input and output interfacing that we need to do, but we also need to generate this ground reference in the middle. The way that I like to generate these ground references, there are a bunch of different ways of doing it. If all you have is a high impedance need for it, you can get away with just using a couple of resistors and maybe some capacitors. So let me do that. We'll do that, and I'll copy another one of those down here. Let's say 10K, value 10K, and I'll copy that one. Value 1 microfarad, and we'll do some math to show this, to prove these numbers in a second. Nope, I lied. Actually, let me do it this way. Okay. 3.3 volts down to ground with a voltage divider that is symmetric, 10K on the top, 10K on the bottom, which means that this point right here is going to be half of whatever this voltage is. So we got 3.3 here, then this becomes 1.65. Did I do my math right? Yeah, 1.65. This becomes a 1.65 volt point. And then the capacitors are there to kind of try and filter out any noise that might be going through there, because we want only DC voltage to go through these resistors. So the capacitors are there. It's called bypass capacitors. The idea being that any AC bypasses around the resistors. These are a 10K impedance, but above a certain frequency, this looks less than 10K, and therefore will be the preferred path for higher frequency audio. How high a frequency, you ask? Well, let's ask our good friend 1 over 2 pi RC. 1 over 2 times 3.114 times R, 10,000, times C, 1 microfarad. Well, that's 1 millifarad, 1 microfarad. Okay, so the cutoff frequency for this RC circuit here is about 16 hertz. That means that at 16 hertz, half of the power will go this way and half of the power will go this way. Below 16 hertz, the power will be, this path will look a higher impedance because capacitors are high pass components, right? So lower frequencies do not pass through a capacitor. Think of 0 hertz DC as the ultimate low frequency, like I talked about in the presentation. 0 hertz is your ultimate low frequency, that is DC. DC will not pass through a capacitor, so but high frequencies will. So at low frequencies, below 16 hertz, this path becomes super high impedance, and this path becomes the dominant low impedance, and this is where all your current passes. Above 16 hertz, it reverses. This path becomes lower impedance, and all of the power will go through this path instead. And so the idea being that this RC filter here is going to filter out any higher frequency noise, higher than our good friend 2πRC calculates. And that's just kind of the like halfway point. Anyway, oh my goodness, we got goofballs in our chat room. Screen share, screen share. Oh, God dang it. Okay. You mean I've been pointing at a thing that you can't see this whole time? Curse, it's not like I don't have my screen right here, right? OBS, I can even see what I'm sharing. And I didn't even pick up on that. This is the problem with doing it live, because if I weren't doing it live, I could just like edit all of this out later. You want me to do that again? All right. 3.3 volts. This point right here becomes 1.65 volts. The capacitor here bypasses all the high frequencies. All the high frequency stuff, this becomes the lower impedance path, and it goes around, straight down to ground. But at the lower frequencies, this becomes the dominant path. Anyway, this creates a voltage reference. But if you have a load that, let's say we have a load over here that is 10 ohms, right? All of a sudden, this becomes 10 ohms in parallel with a 10K ohm becomes 9.999 ohms, right? The 10 ohms becomes dominant. This one pretty much disappears. So now you have a 10 ohm in series with a 10K ohm, and your voltage divider has moved away from 1.65. This drags down the thing. So the point being that this center point moves up and down with the current that you draw from it. So as long as the impedance of these two resistors is small relative to the load that you're trying to drive, it works okay just as it is. But we can't be sure that that's going to happen. So instead, I am going to put an op amp here. TLO72. I'm not actually using a TLO72, but this is just the their pinout is the same, so it doesn't matter which op amp I actually put in the schematic. So what I want to do is I want to use this op amp for its ability to lower the impedance of a signal. I'm not going to go into the details. You should use 0.1 ohm resistors for your ground reference. You mean for these here, Kenneth? Because that would draw an awful lot of current. I could make these super low impedance, like 10 ohms, and then I would have 20 ohms from 3.3 volts to ground, but that would just draw an awful lot of current and would be a lot more current than, it would be... It's just burning up these resistors. It doesn't do any good, or it doesn't get used for a whole lot. So it's a much better, much more efficient system to do it with this op amp. I'm not going to go into op amps tonight because I've already been streaming for way too long. And I had problems with getting the stream started tonight, and I had problems with the screen tonight. So I'm not going to go into op amps tonight. We are going to just trolling the live stream. Thank you, Kenneth. I'm going to throw peanuts at you. Peanut gallery. I'm going to ask you to accept on faith the circuit I'm about to design for this op amp. We will go into op amps in a different episode. So we are going to use this op amp in what's called a voltage follower mode, which is a very boring mode where there is no gain whatsoever. We connect the output directly back to the input, and then to the negative input, excuse me. and then we connect the voltage that we want to replicate to the positive input. This is called a voltage follower. It's unity gain. Gain is 1, which means it doesn't have any gain at all. The output is 1 times the input signal. But what it does is it presents a very high impedance load to this circuit, like megohm, tens of megohm, right? So this draws very, 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 very little current, which means that this circuit here is very stable. It doesn't matter how much current is drawn out here. The op-amp provides all of that current. All the op-amp needs is a reference voltage on the input. And so now I can draw as much current out here as I want. So let me get my 10 ohm load back. So copy 10 ohms. So let's say that 10 ohm load that brought this voltage way down, that 10 ohm load, that current is being provided by the op-amp, the power supply connection to the op-amp, which I haven't shown yet. Let's go ahead and do that. It's unit C. Normally that goes right there on the schematic, but kind of bugs me because it pushes the rest of my schematic way out of the way. Right? So all the current to that 10 ohm resistor is being provided by that power supply and that ground connection. None of it comes from this input right here. I think it's safe to say none. If it isn't none, then it's like meg ohm amounts of current is provided from this circuit. So this voltage reference is super duper stable, and the op-amp is responsible for providing all of that current. So what we're going to do, what we've basically done is that we've created this line right here. I'm pointing with my finger, but this line right here will be a super stable half VCC output. With 3.3 here, this becomes 1.65. If this were a 5 volt input, or more importantly, if this were a 5 volt input, this would be 2.5 volts, right? Whatever your power supply input is, this creates a strong, solid, low impedance output that is halfway between it. And now we can use that halfway between our voltage rails as our false ground. So I'm going to call this analog ground, ground A. Okay? So this is a signal that we have created. I'm calling it our analog ground. We are going to use this as our ground reference for all of the active circuits in the middle of our board, of our project. We still have to interface with real honest-to-goodness ground on the inputs and on the outputs, and we'll take care of that later. This ground, the input signals are going to be referenced around this ground, but we're going to move them up to VCC over 2. We're going to do our stuff to it, and then we're going to move them back down to ground on the output. That's how we get away with not needing a negative voltage supply. So that's power. Let's take a look at what we did again. I want to be able to power this either over USB or some other internal or some other connector. And we just need a voltage input, but this power is incredibly noisy, especially if you get it from USB. So we want to do some filtering, and the filtering we're going to do, I tried on my circuit, I just tried using an RC circuit, and it was not enough. I got the USB coming in here, there's a 10 ohm resistor and a 220 microfarad, 220 microfarad cap. I was hoping that would be enough. Nope, my work laptop is incredibly noisy. So instead, we're going to put a 3.3 volt regulator here, and that regulator is going to force, no matter what voltage comes in on the input, it's going to force a very clean, precise 3.3 volts on the output. And then we've got some more filtering here. The 10 microfarad is actually there because the voltage regulators need some capacitance on the input and output to remain stable. But they also provide, for mic level, it doesn't matter because you're not going to be driving much current at all. But if you are driving headphones or speakers, those require large bursts of current for certain high energy sounds that come through it, like a boom, like a big loud boom or a crash hit or something like, mostly bass, or plosives like those are very high energy things, and for them to be able to reproduce those accurately, they need to be able to get a lot of current very quickly. And to do that, you need to have a very low impedance source of current very close to the amplifier. And that's generally done by very large capacitors with low ESR, effective series resistance is what it's called. So you want very low ESR, very large capacitors, very close to your amplifier components. And I did all of that on my headphone amplifiers, but we're not going to be doing it here. Mic level is so low power that 10 microfarads and a 0.1 microfarad cap in parallel are plenty. So that gives us our 3.3. And then we use that 3.3 and a voltage divider to give us a half VCC reference in the middle with a little bit more filtering around the outside, just to keep this super clean. And then we send that into the input of 1/2 of the op-amp chip that we're going to be using. And the op-amp is just configured as a voltage follower. Whatever the output voltage is, or excuse me, whatever the input voltage is, it will set the output voltage to that. Again, take it on faith that what I've built here is a voltage follower. We will explain op-amps in a later episode. And then the output of that is a very low impedance, very strong, solid, half of VCC signal. And we're going to use that as our ground reference a little bit later. So I'm going to stop tonight here. We're just getting started, and we're going to build some more cool things. For those who are later to the stream, this is a microphone splitter, or at least I started prototyping it tonight. The power supply is incredibly noisy, so we're going to improve that, and that's what we're talking about here. I'm done with the schematic, so I can go back to this. The power supply on this is incredibly noisy, so that's what we're fixing tonight. But the idea is that there's an op-amp right there. We already showed how we're using half of that op-amp. The op-amp is going to be taking the microphone input signal, amplifying it, and then we're going to isolate it with some transformers and some other things, and then send the mic output to multiple destinations. That's it. That's what we're building tonight. I don't see any questions in the chat. Just people telling me that I had the camera on and was not showing my desktop. Thank you very much for doing that. Yeah, and I called Kenneth a goofball. Who's the goofball? Anyway. Let's hear. Joel Hudson corrected me and said that it is P equals IE instead of IV. I will go back and forth on this one. I do not feel religiously one way or the other on this. Joel is correct. The actual variable that electrical engineers use to represent voltage is E, echo, not V as in Victor. It is the electromotive force. But I don't care. I'll go back and forth. P equals IE is easy to remember, so power equals current times voltage. Pi, PIE, that's nice. But I usually say P equals IV, but I will sometimes say E equals IR, Ohm's law, or V equals IR. I'll go back and forth. E is more correct. V is often what I say. Deal with it. I apologize, but I'm sorry, not sorry. But okay, let's talk a little bit about the equations. The three equations we're going to be using a lot in here are Ohm's law, E equals IR, voltage equals current times resistance. Power law, P equals IE, power equals current times voltage. And then the frequency law. I don't know that it's a law so much as a calculation, but F equals 1 over 2 pi RC. The frequency equals 1 over 2 times pi times the value of the resistor in ohms times the value of the capacitor in farads. So if you need to do microfarads, it's, like 1 microfarad is 0.000001, right? So you need to make that in farads. Those are the three equations: Ohm's law, power law, and then the frequency cutoff point for RC circuits. It also works for RL circuits, by the way. So if you're doing an inductor, the exact same function, 1 over 2 pi RL will work for that one. It gets a little bit more complex when you're doing LC circuits, because then you need to take a square root, and I don't remember that one off the top of my head. We're not going to be dealing with any LC circuits in the audio stuff that I'm dealing with here. You certainly can, we're just not going to. But those are the three equations that we're going to be using, and I use them a lot. 1 over 2 pi RC is something that I will throw annotations on my schematic for all the time. Like, I'll actually give you an example of that right now. So to show that I've done the math on this, 1 microfarad times 10K equals 16 hertz. Right? So I'll throw that little annotation right next to the 1 microfarad and the 10K equals 16 hertz. And that came from this one. 1 over 2 times pi times R, that's 10K, yep. And then the capacitor is, that's a point, excuse me, that's a 1 microfarad. And that came out to 15.923. When you see lots of ones, it's always 1.6 times 10 to the something. So 1 microfarad and 10K is 16 hertz. So that's where that came from. All right, I said I was done. We're going to cut it here for this episode. Thank you very much for watching, and pay attention. We're going to be continuing to do more. I don't know what I'm going to do next. Probably the inputs to this, and maybe even the op amp to show how we're using the op amp and whatnot. So we'll do that in the next episode, and then after that we'll talk about the outputs. But I do want to take an episode to talk about, it'll probably be the next one actually, because if I'm going to put the op amp on the schematic, that'll be the time to talk about op amps. Yeah, so thank you. I'm Smitty, Smitty Halibut on Twitter, at Smitty Halibut on Twitter. If you have any questions or comments, feel free to leave them below in the comment section below, or you can hit me up on Twitter. I probably respond to that a little bit faster. And yeah, until next time, thank you so much, 73, and be good humans. We especially need a lot of that right now. So go out and be awesome, build awesome things, share what you're building if you can, and yeah, have a great day, everyone. Thank you so much. And then this is the awkward thing where I'm waiting for the screen, the stream that I'm looking at to do the goodbye, and then I had to hit the stop button. All right, I think I'm good. Cheers, everybody.